Long before mathematics became a series of abstract symbols on a chalkboard, it was a practical tool for survival. It began when humans started noticing repeating sequences in the seasons, counting objects for trade, and measuring the land beneath their feet. Even today, we meet these principles before we can speak. A child stacking blocks is performing a series of physical experiments, testing gravity, checking alignment, and observing the immediate consequences of every small adjustment. The modern world makes this kind of quiet observation difficult. Our attention is constantly pulled away by a stream of alerts, metrics, and glowing screens. This constant interruption keeps us from noticing the basic truths that wait without noise. When we skip the act of observing how small things interact, the technology built on those interactions starts to feel like magic. Skipping the foundation is what makes modern algorithms feel so alien and intimidating. It leads to a gap in our understanding. We see the child with the blocks on one side and a machine that can predict human language on the other, but we rarely see the steps that connect them. To bridge that gap, we use first principles. This approach refuses the complex explanation and returns to the smallest working parts of an idea, the facts that cannot be broken down any further without becoming false. From this perspective, even the most advanced AI is not a monolith. It is a structure built by stacking simple, observable truths. When the knots of a complex problem are separated into these smaller pieces, the mechanics become approachable. Understanding this ladder of principles allows us to see how a machine arrives at an answer. It moves us from a position of blind acceptance to a position where we can actually inspect the work and verify if the logic holds. First principles thinking strips away the mathematical jargon and looks at the rule connecting the input to the output. At its core, machine learning is a method for making relationships precise enough to reason with. This geometric model shows how a computer handles abstract ideas, mapping words as coordinates based entirely on context. Closeness represents meaning. By calculating vector differences, the system uses geometry to determine that king relates to man the same way queen relates to woman. This pipeline illustrates the continuous loop of input, math, decision, and improvement. Raw data enters the system and passes through a mathematical function, turning human preferences into a numerical prediction. If the prediction is wrong, it uses that error to update its internal rules. What looks like understanding is actually this structured geometry iterating over time. The machine isn't thinking in words, it's finding a path through coordinates that has proven successful in the past. The mechanism that allows the system to learn from its mistakes is called backpropagation. It's how a correction at the end of the process travels all the way back to the beginning to update the rules. Imagine a pulse of light traveling through a series of rooms. When it reaches a dead end, it sends a colored signal back through the exact same trail, marking every gate that needs to be adjusted for the next attempt to succeed. By repeating this correction millions of times across massive datasets, the system learns to generate sentences and images that appear remarkably realistic. But we have to distinguish between fluency and comprehension. A machine can follow the mathematical path to a correct-sounding sentence without having a life, a conscience, or any actual experience of the words it uses. The danger is a psychological one. Humans are evolved to infer a mind from behavior. When we see smooth language, we instinctively supply an inner life where none exists, projecting wisdom onto a system that is only calculating probabilities. As these systems become more capable, our scrutiny tends to relax. When a machine works well enough, we often stop asking how it reached its conclusion, allowing its performance to mask its lack of judgment. Mistaking the scale of a system for the quality of its wisdom is a human error. High performance does not make a system responsible. It only makes the human design decisions behind it more consequential. AI systems are abstraction engines. To make the world computable, they must compress the messy reality of human life into rows, features, and scores. In that process, context is inevitably lost. The builder and the user must continually ask what has been removed in that compression. If we only look at the score, we may miss the human reality that the numbers can no longer represent. Automation doesn't remove responsibility, it concentrates it. Every automated outcome is shaped by the initial human decisions about what to measure, what to ignore, and what counts as a success. A system optimized for a narrow mathematical target can produce results that are locally correct but globally harmful. It will pursue the score it was given, regardless of the consequences that were left outside the model. Even an autonomous system operates within a world designed by people. Its actions are delegated, meaning the human designer remains answerable for the system's impact on the real world. To manage this, we can use a mental compass. Before adopting a tool, we check it against 4 points. Does it serve our purpose? Does it match the present reality? Does it respect our constraints? And is there evidence we can actually verify? This journey from basic observation to advanced AI is a single connected thread. Every capability we build, from simple patterns to complex agents, must be anchored in these foundational principles. The recurring theme is that understanding doesn't come from memorizing jargon. It comes from disciplined noticing, identifying the simple truths beneath the complexity, and then building responsibly from there. The goal is to move beyond being a passive user of technology. By returning to first principles, we can enter the technical world with clear questions and a specific ethical framework for our own choices. The final purpose of studying these systems is not just to see what a machine can do. It is to ensure that human judgment remains the final layer, identifying the boundaries of the engine and deciding what is actually worth doing.